Welcome to the SmartKeys podcast. Usually when we picture digital work, we kind of imagine it as something entirely weightless. We talk about the cloud like it's this infinite abstract space where our data just, floats seamlessly.
Right, yeah. The terminology we use definitely reinforces that illusion. I mean, we use words like wireless or virtual, which completely detach the end product from the actual massive industrial machinery that's running quietly in the background.
Exactly. You send an email or stream a video or ask an AI to draft a report, and it just happens. The physical world barely seems involved at all.
But the physical infrastructure, the thousands of miles of copper wire, the heavy-duty transformers, the millions of gallons of water for cooling, is the actual physical engine of the digital revolution.
And when you start pulling back the curtain on that engine, the cloud starts looking a lot less like magic and much more like, heavy industry.
Oh, absolutely.
That's really what we are getting into today. We are looking at a landscape where the physical, invisible power grid is literally dictating the future of digital work.
Which is a massive paradigm shift for anyone running a digital business right now. Historically, business leaders compared cloud providers based on two very simple metrics: price and latency.
Right, like which server farm can run my software a fraction of a cent cheaper? Or which one will ping back to my customer a millisecond faster?
Exactly. But the parameters of that decision have completely changed. It's not just about speed and cost anymore.
Because today's deep dive is fundamentally about the hidden massive cost of deploying artificial intelligence at scale, specifically the cost of electricity.
It's the new bottleneck.
It really is. And we are using an incredibly insightful article by Felix Römer from smartkeys.org titled AI Data Center Energy in 2026, What It Costs Your Business.
It's a fantastic piece.
So our mission for you, the listener, is to unpack this very comprehensive resource. We want to translate these macro energy trends into micro business impacts and, extract actionable strategies to keep your business ahead of the curve.
Because the strategic question for modern professionals is no longer just about software optimization. It is entirely about power availability. The new metric is whether the local electrical grid can actually deliver the megawatts required to run these highly intensive AI tasks and do it on the schedule your business needs.
I want to explore that bottleneck, but first, I'm kind of tripping over this fascinating contradiction in the data here. Because as an individual user, AI usage feels unbelievably cheap. It feels completely frictionless.
Oh, for sure.
Like if I type a prompt into an AI model, my laptop battery doesn't immediately drain. It feels low impact.
And that intuition isn't entirely wrong, well, on a micro level anyway. To put some actual numbers to it, Google published a report analyzing the energy footprint of their Gemini model.
Okay, what did they find?
They found that a median text prompt uses about 0.24 watt-hours of electricity. It also consumes a tiny fraction of a drop of water for cooling around 0.26 milliliters.
Wow, that is tiny.
Yeah, and other estimates from groups like Epoch AI and OpenAI land at a very similar ballpark, placing a typical short query around 0.3 to 0.34 watt-hours.
So just a fraction of a watt hour. How does that compare to something we use every day? I mean, for context.
Think of a standard, old-school 60-watt incandescent light bulb. Leaving that bulb on for just 1 minute uses a full watt-hour.
Okay.
So a single AI prompt uses about a quarter of the energy required to keep a light bulb on for 60 seconds. It is a minuscule amount of power.
Okay, so on an individual basis, it's practically a rounding error, but it's like death by a billion paper cuts, isn't it?
That's exactly what it is.
Because when we zoom out, the global numbers are terrifying. The article mentions these staggering projections, but I have a hard time wrapping my head around how we get from a fraction of a watt hour to a literal global energy crisis. How big is the actual macro footprint?
To understand the footprint, we have to look at the latest figures from the International Energy Agency, the IEA. They reported that global data center consumption hit roughly 415 terawatt hours in 2024.
415 terawatt hours.
Right. That represented about 1.5% of all the electricity generated globally.
Which already sounds huge.
It is, but the growth curve is what actually has the industry alarmed. The IEA's base case projects that number reaching roughly 945 terawatt hours by 2030. They're expecting demand to more than double in a span of just 6 years.
More than double. That is a massive spike for physical infrastructure to absorb in such a short window.
And regional concentrations make it even steeper. The Berkeley Lab modeled the United States specifically, projecting that data center usage could jump from making up 4.4% of national electricity demand in 2023 all the way up to 12% by 2028.
Up to 12% of the entire U.S. power grid dedicated just to data centers. That's wild.
And if you look even further out, Deloitte forecasts U.S. data center demand hitting 176 gigawatts by 2035, with AI surging from just a small slice of that pie to making up a massive 70% of the total load.
Okay, so explain the mechanics of this to me. If one query is a fraction of a light bulb's energy, how on earth are we arriving at nearly 1,000 terawatt hours globally?
Well, the mechanism driving this comes down to the difference between training an AI model and running inference.
Okay, break that down.
Training is the initial heavy lift. That is when engineers feed a model mountains of text and data, forcing the neural network to adjust its internal weights billions of times until it learns to recognize patterns. That takes massive power, but it's a periodic event.
Right, you train it once or at least infrequently.
Exactly. Inference, on the other hand, is the continuous operational phase. Every single time you or any other user asks the model a question, it runs inference.
Ah, so it's the sheer volume of continuous querying happening around the clock.
Yes. Consider the math of millions of users, and soon, billions running inference simultaneously 24 hours a day. And the queries themselves are becoming vastly more complex.
How so?
While generating a simple text response is relatively cheap, but asking an AI agent to read a 100-page PDF, extract data, format it into a table, and then generate an accompanying image, that requires exponentially more matrix multiplications under the hood.
So the compute load just stacks up rapidly.
Crucially, all of this AI usage is additive. We haven't stopped streaming movies or running standard SaaS tools or processing digital payments. We are just layering a massively compute-intensive technology directly on top of our existing digital habits.
So the demand is skyrocketing across the board. If I am looking at this from a purely economic standpoint, the logical next step is just to build more supply.
Right.
Like if we need more computing power, we just build more data centers.
You think so?
But the article makes it incredibly clear that the problem isn't a lack of capital and it isn't a lack of technology.
No, the underlying technology to generate power exists. The capital to build data centers is absolutely there. Tech giants are sitting on mountains of cash. The true bottleneck is the physical electrical grid itself.
It's all about timing, right?
Exactly. It is an issue of timing. The grid simply cannot expand fast enough to meet the extremely aggressive timelines of these tech companies.
Which brings up a stat from the source material that genuinely blew my mind. There is roughly 2 terawatts of generation capacity currently sitting in U.S. interconnection queues.
It's a staggering number.
2 terawatts, just waiting for permission to connect to the grid.
For context, the entire currently installed power fleet in the U.S. is roughly 1.2 terawatts.
Wait, really?
Yeah. So we have nearly double the country's existing power capacity waiting in bureaucratic and engineering limbo.
That is just insane. What's causing the holdup?
The delay comes down to severe supply chain roadblocks for the heavy physical equipment required to safely step down and route that power. We're talking about critical components, mostly things like transformers and switchgear.
I always hear about transformers being an issue, but what exactly is holding up the manufacturing? Like, why can't we just stamp out more of them in a factory?
Because high-voltage transformers aren't simple gadgets you just roll off an assembly line. They are massive, highly customized pieces of heavy engineering.
Okay.
They consist of thousands of layers of specialized electrical steel wrapped in massive copper coils, insulated with specialized paper, and then submerged in huge tanks of oil.
Oh, wow. So it's a huge undertaking to build even one.
Right. They require highly skilled labor and immense raw materials. And because of the sudden surge in demand, the lead times for these components have stretched from a matter of months to several years.
Okay, so it's like buying a fleet of cutting-edge Ferraris, your ultra-fast, state-of-the-art AI chips, but you are stuck at a 5-year-long red light on a 1-lane dirt road.
That's a great analogy.
The cars have the horsepower, they're fueled up and ready to go, but the physical infrastructure beneath them just cannot handle the traffic. What does this actually mean for a company trying to build out a new data center?
It means that a fully funded project, with the land already purchased and the servers ready, can still slip its launch date by years just waiting for a grid study and a substation upgrade.
Just waiting in line.
Exactly. And looking at national averages really masks the severity of the problem because data centers tend to cluster together to share fiber optic networks and specialized workforces.
Right, they all want to be in the same hubs.
And they run flat out 24 hours a day, which places intense, hyperlocal stress on the grid.
The article highlights Ireland as a prime example of this local concentration risk. Data centers consumed an astounding 23% of Ireland's metered electricity in 2025.
It's incredible.
Just let that sink in for a second. A single industry using nearly a quarter of a sovereign nation's power.
And the situation in the U.S. is experiencing similar localized strain. Northern Virginia's Dominion Energy Zone is the world's largest concentration of data centers.
Data center alley, right.
Yep. And in a recent resource plan, they reported fielding contracts for an additional 47.2 gigawatts of demand. They were forced to raise their load forecast by 17% in less than a year.
That kind of localized spike has to have consequences.
It does. When you have that much concentrated demand, it causes physical stress on the wires.
Yeah.
It leads to load relief warnings, voltage sags, and basically frantic scrambles to reinforce aging infrastructure before the lights go out for the surrounding neighborhoods.
Okay, wait, let me stop you there because I'm putting myself in the shoes of the listener right now. Say you run a mid-sized e-commerce brand or, a digital marketing firm. You don't own a data center. You just lease software and use cloud services. Why on earth should you care if some massive transformer takes 3 years to arrive in Northern Virginia? Why does this matter to the bottom line?
Because the costs of those delays and those infrastructure upgrades will inevitably arrive on your desk. You won't get a bill for a transformer, obviously, but you will see it reflected in your cloud computing pricing, your colocation rates, and your commercial software tariffs.
So it trickles down.
Heavily. When major cloud providers are forced to pay 2.5 times more for electricity from a newly built gas-fired power plant, or when they have billions of dollars tied up in a site that they can't even energize for 5 years, they do not absorb those losses.
Right, they pass the premiums directly down the chain to the end users.
Exactly.
So the meter might not be spinning in my office basement, but my business is still footing the bill for it.
You definitely are.
But surely we've faced computing scale issues before. Like, for years, didn't data centers just get more efficient to offset the growing energy demand?
Historically, yes, they did. The industry relied on facility efficiency to mask the growing power draw of the servers. But the era of easy efficiency gains is officially over.
Over. Why?
Well, we measure facility efficiency using a metric called power usage effectiveness, or PUE. It's a simple ratio. You take the total amount of power entering the facility and divide it by the power actually used by the IT equipment.
So a perfect score is 1.0, meaning every single watt goes into computing and 0 goes to cooling or lighting.
Exactly.
And where does the industry stand right now?
The Uptime Institute's 2025 survey showed that the average PUE is stuck near 1.54. It has essentially flatlined for the past several years.
So we hit a wall.
We squeezed all the easy inefficiency out of the building designs. But the new AI chips are incredibly power dense. They draw massive wattage and generate intense heat in a very concentrated physical space.
The facility overhead, like the giant air conditioners and the fans, just isn't falling fast enough to offset how hot these new AI chips run.
Exactly. And that rising power demand triggers another massive bottom line impact that businesses often completely overlook: environmental reporting.
Oh, right.
Most modern businesses are held to strict climate frameworks now, often tracking their Scope 2 and Scope 3 emissions.
Scope 2 being the indirect emissions from the electricity a company buys, and Scope 3 being the emissions up and down their entire supply chain, which includes the cloud vendors they use.
Correct. And here is the brutal reality of carbon accounting. Efficiency does not equal decarbonization.
What do you mean by that?
If a cloud provider builds a highly efficient data center, but the utility company powers it by firing up an old coal plant to meet the demand, your company's carbon output spikes.
Oh, wow. So it doesn't matter how lean your software code is if the physical plug ultimately connects to a fossil fuel source.
Right. Your carbon accounting software will flag that spike immediately, which can jeopardize corporate sustainability goals and investor relations.
So AI expansion is no longer just an IT upgrade.
Not at all. It is a fundamental risk management and digital procurement challenge.
Okay, so the picture is clear, and it's a bit daunting. The grid is jammed, costs are trickling down, and emissions reporting is becoming a minefield. Let's pivot to the solutions.
Yes, let's look at what we can do.
How can modern professionals actually optimize their operations right now to stay ahead of this? What practical workarounds are outlined in the source material?
The most immediate and powerful lever businesses control is workload efficiency. Cost control for AI cannot be siloed in an IT department anymore, or treated as an afterthought by a sustainability committee.
So where does it belong?
It has to be a core part of your large language model operations strategy.
And what does that actually look like in practice for a software team?
It requires a fundamental shift in how developers interact with the models. First, it means intelligent routing.
Intelligent routing.
Yeah, you do not need a massive, power-hungry, trillion-parameter model to answer a simple customer service FAQ. Developers need to route simple requests to smaller, highly efficient models.
That makes total sense.
Second, you implement robust caching. If your users ask the exact same question 1,000 times a day, you shouldn't compute the answer 1,000 times. You compute it once, store it, and recall it for the other 999 users, bypassing the heavy inference load entirely.
Okay, the outline also mentions batching and quantization. Now, I get batching grouping non-urgent tasks together to run them efficiently overnight, but what is quantization?
Quantization is a really fascinating mathematical trick. Inside a neural network, the parameters are typically stored as very precise, complex numbers, usually 32-bit floating point numbers.
Okay.
They take up a lot of memory and require immense processing power to multiply together. Quantization is the process of compressing those numbers down, rounding them off to much simpler 8-bit or even 4-bit integers.
Ugh, like taking a massive, high-resolution raw photograph and compressing it down to a small JPEG file. It looks almost identical to the human eye, but it takes up a fraction of the storage space.
That is a perfect way to visualize it. By mathematically compressing the model, it requires significantly less memory bandwidth and computational power to run inference.
Which directly translates to massive energy savings with minimal loss in actual output quality.
Exactly.
It requires a massive mindset shift, though. It's realizing that optimizing your software code, making it leaner and smarter, is actually the most effective way to lower the physical real-world utility bill.
It is. Your software developers are essentially acting as your new energy managers.
That's a wild thought. But what about the physical hardware side? If traditional air cooling is failing, how are they keeping these server racks from literally melting?
Facilities are being forced to abandon traditional air conditioning for these dense AI racks and move to liquid cooling.
Just pumping water through the servers?
Yeah. Basically, yes. This usually takes two forms. The first is direct-to-chip cooling, where tiny tubes of cold liquid run directly over the processors.
Okay. And the second?
The second, more extreme method is immersion cooling, where the entire server rack is literally lowered into a bubbling tank of specially engineered, non-conductive dielectric fluid. The fluid boils, pulling the heat directly away from the electronics.
That sounds like straight out of science fiction, but the article points out a major trade-off with these liquid systems, right? It involves water consumption.
It is a critical trade-off. Liquid cooling can drastically slash the electricity required to keep the servers at operating temperature. But eventually, that hot liquid has to be cooled down again.
Which takes water.
Yes, which is often done outside the building using massive evaporative cooling towers. These towers consume millions of gallons of water.
So if a business is relying on a data center located in a water-stressed region, like the American Southwest, trading electrical efficiency for massive water consumption is a really dangerous ecological and public relations bargain.
Precisely. Equipment choice now ties directly into life cycle costs and environmental reliability.
There is one more workaround the article explores that I thought was absolutely brilliant, and it solves the physical grid problem using pure software. Workload mobility.
Workload mobility is perhaps the most underutilized strategy available today.
How does it work?
We usually assume all computing has to happen instantly, right where we are. But many AI tasks, like training a new model, processing massive batches of data, or running complex simulations, they are flexible in terms of timing and location.
Okay.
Modern software orchestration layers can automatically detect where on the global grid electricity is currently abundant, cheap, and generated by clean sources like wind or solar.
So if the wind's blowing hard in Texas, but it's calm and expensive in Virginia, the software just routes the computing job to Texas. It's literally chasing the weather to find cheap power.
Exactly. It shifts the heavy compute loads across continents to follow the sun or the wind. It's an incredibly elegant way to bypass a localized hardware constraint by using intelligent software routing.
Bringing all these insights together, how should a business leader actually plan for the future? We've talked about macro data, physical grid constraints, and software workarounds. What is the cohesive strategy here for our listeners?
The most crucial takeaway for strategic planning is to abandon the reliance on single-point estimates.
Meaning what, exactly?
Well, when a major consulting firm says demand will hit exactly 176 gigawatts by 2035, you cannot treat that specific number as a concrete foundation for your capital planning. The variables are just too volatile.
Right.
Businesses must build demand scenarios using broad ranges. The rate of AI adoption, breakthroughs in chip efficiency, or a new delay in transformer manufacturing will all shift the final reality. Assuming linear growth in this sector is a recipe for disaster.
Because if your entire operational roadmap relies on a specific local grid having capacity by exactly 2030 and it slips to 2033 because of a supply chain issue, your product launch is dead in the water.
Which leads directly into the second strategic pillar. Businesses have to start treating utility companies and grid operators as partners in their ecosystem, not just as vendors on a checklist.
That's a huge cultural shift for tech companies.
It is, but if you require massive computing power, you have to initiate interconnection conversations years in advance. Engaging with regulators and understanding the physical limits of the local grid early on saves infinitely more time than trying to negotiate a clever procurement trick later.
That makes total sense. Shifting from a transactional relationship to a collaborative one. The source material also mentioned demand response programs as a way to collaborate. How do those work?
Demand response is a massive opportunity that is currently being largely ignored. Right now, fewer than 5% of data center facilities participate in these programs.
Why so few? What is it?
Essentially, it is an agreement between the facility and the utility, where the data center promises to voluntarily lower its power usage during peak grid events.
Okay, so like during a heat wave.
Exactly. Imagine a severe heat wave rolls through a city, and everyone turns on their air conditioning. The grid is pushed to the brink of a blackout. A data center participating in demand response receives a signal, and their software automatically pauses non-urgent AI training jobs.
So dropping their power draw by, what, 20% for a few hours to help stabilize the neighborhood grid?
Yes, even though 10 to 30% of a data center's load can be flexed, very few actually do it.
And in return for being flexible, they probably get better pricing or faster approval to connect to the grid in the first place.
That is exactly the incentive structure. Grid operators are much more willing to approve new interconnections for facilities that act as shock absorbers rather than inflexible drains on the system. It all comes down to realizing that you do not ultimately control the infrastructure you depend on.
It is a humbling realization for an industry used to moving fast and breaking things.
It really is. And it raises an important overarching question, something for you, the listener, to mull over as you think about the future of your own business strategy.
Let's hear it.
Historically, the constraint on digital innovation was the cleverness of the code or the speed of the silicon. But as physical electrical power becomes the ultimate binding bottleneck of the 21st century, we might witness a massive paradigm shift.
What kind of shift?
The most valuable tech companies of the next decade might not be the ones designing the smartest algorithms or the fastest chips. The real winners might be the companies that figure out how to become their own hyperlocal utility providers.
Wow. Turning localized energy generation, advanced battery storage, and microgrid management into the ultimate technological moat?
Exactly.
Because if you can generate and manage your own clean power on-site, you completely insulate yourself from the grid's delays. You control your own destiny.
The physical infrastructure, the ability to generate and deliver a reliable electron, becomes the ultimate competitive advantage in a digital world.
That is a phenomenal thought to end on. We started this deep dive talking about how digital work feels weightless and how we are conditioned to assume the cloud is just this infinite abstract space.
Right, the illusion of the cloud.
But to keep those AI models learning and to keep that digital engine turning, you have to understand the physical realities of copper wire, massive transformers, and grid capacity. The businesses that understand that the digital revolution is entirely dependent on heavy physical infrastructure are the ones that are going to thrive.
Absolutely.
Thank you so much for tuning in to the SmartKeys podcast. We really appreciate you spending your time with us, looking past the software interfaces and diving into the physical nuts and bolts that are actually driving the future of work.
It's been great.
If you want more insights that bridge the gap between technology, physical infrastructure, and business strategy, make sure to hit that subscribe button. And I strongly encourage you to read the full source article by Felix Römer. It is packed with even more nuanced data, regional breakdowns, and strategic insights that we just didn't have time to cover today. You can find the link to the full piece on smartkeys.org right in the show notes. Until next time, keep looking behind the curtain and keep asking how the machine actually works.